All right, and in this video, they ask us to take the limit as x approaches 2 of the absolute value of x minus 2 divided by x minus 2. Now, this is a very common limit type of problem. You'll see lots of different exercises that have the absolute value of some expression divided by the same expression, and I just want to show you what to do here. Now, we can evaluate this limit 3 different ways. We can evaluate it numerically, which is what we'll do first. You can evaluate it graphically by putting it on an XY axis in the coordinate system and graphing it and seeing what the limit is. Or we can do it analytically, and the way we would do that is write it as a piecewise function and go that route. But we're going to start with looking at it numerically. Numerically means we're going to put it in a table. So here I've pulled up my TI here, and I went ahead and plotted it or entered it in the y equals menu here. And you can go to second table set, and if you want to automatically generate the XY values, you can just set both of these to auto, and then make it start at 2, and then just set the width of each individual X value to be like 0.1 or 0.01 or something very small. But instead, I'm going to make it ask me what I want the X to be and let it automatically generate what the Y is. Y is your dependent variable because it depends on your choice of X, which is the independent variable. So let's go to the table. Okay, we'll just pick some values around 2. We'll pick like 1.7, 1.8, 1.95. It doesn't have to be anything specific. Just pick values very close to 2. We'll try it at 2. Now you see at 2 there's an error, and we knew that actually before we started the problem, because if you try to take 2 and plug it in this expression, you get 0 divided by 0. That's an indeterminate form. But after 2, we have like 2.05, 2.1, 2.2, any values very close to 2 but larger than 2. Here's what we get from our table, from our XY table. I'll cut that out so I can blow it up for you. Okay, so here we go. All right, so here we go. So before 2, it looks like the values are -1, -1, -1, -1, and above 2 looks like they're +1, +1, +1. Now, why would that be the case? Well, let's just think about this logically for a minute. If you pick a value larger than 2, it doesn't matter how large, but just any value larger than 2, then the difference of x minus 2 will be positive, right? Because x is bigger than 2 based off of your choice. But the absolute value of a positive number stays positive, in which case it'll be the exact same as the denominator. And so you might get 5/5, 6/6, 7/7. So anything you plug in larger than 2 will give you 1. Now anything less than 2, this difference here would be negative, which means the denominator would be negative, but the numerator will be the same numerical value except positive. So those would cancel, but would leave you with -1. So what does that seem to indicate about the limit? There's not one definitive numerical value that the function approaches from both sides of 2. So this would be an example where we say the limit does not exist. Now we use this expression so often, and a lot of limits do not exist, that we typically abbreviate this capital DNE, which obviously stands for does not exist. Now, just in closing, I'll show you a couple of other things as well. If we wanted to do this graphically instead of numerically, we could do the same thing. We could either graph this on our TI, and you can kind of see the graph down here at the bottom, or I'll graph it right here. From the left of 2 is -1, and from the right of 2 is +1. And so we see the y values do not go to the same place, or to say it another way, the limit from the left-hand side does not match the limit from the right-hand side, so the overall limit would not exist. So we have this sort of graph going on here, open dot at 1, at 2 of a y value of 1 going to the right, and then an open dot at 2 with a y value of 1 going to the left. So again, we see that the limit does not exist.